for new construction, but we can't do that without talking about what's in new construction and what that actually looks like, at least according to the building code. This is evolving. I'm involved in on some of the committees talking about changes to the building code for 2025. Who knows where that stuff will go, but let's see what we've already got. Oops, no, I'm drawing from there. Hang on a second. Okay, there we go. Okay, yeah. We can't start a radon presentation without a quick introduction to radon, but that's only one slide. And then we're going to go straight into the building code considerations. Oh, you know, this whole thing started maybe 15 years ago or so because I built this net zero energy house for myself. I'm still building it. It's been 15 years and counting, and I'm still working on it. I do most of the work myself. Very painful process, but I built a net zero house. It was energy efficient and airtight and well insulated, and I never crossed my mind I could possibly have a radon issue until I tested, and of course I had a radon issue. When I looked into getting it mitigated, there was basically no one around that could do that, and I had to stumble through the process myself, eventually get certified, eventually become a trainer, and now here we are. It's my thing. So radon can be anywhere. Radon's a radioactive gas. It comes from the soil. You can't detect it with your senses. You can't see it, taste it, or smell it, but it gets sucked into houses where it can build up to kind of sort of dangerous concentrations. The hazard is long term. It's not like carbon monoxide. It's not going to kill you overnight in your sleep. It's a lung cancer hazard. That's obviously very bad, but it's over the course of your lifetime. So some people take it more seriously than others, but it is a thing. And we do have an action level from the federal government that says, hey, if your house gets over a certain level of radon gas, which is 200 becquerels per cubic meter, you should do something about it. But it's optional. It's optional for homeowners to do anything about it, except if you have employees that work there, they have the expectation of safety, so generally you'd expect it to fix it. Or if you rent out the building, probably that they'd expect some mitigation. So the first thing is there's a myth that new construction rough-ins are mitigation systems, but of course they're not. Rough-ins are not mitigation systems. They're just rough-ins. In the same way you can't walk down to the basement and take a shower with your shower rough-in downstairs. It's just a pipe in the ground. Radon rough-ins are not systems. They're not active. They're not working. They're just waiting for you to connect some depressurization equipment. So there is a myth. A lot of people think because they have this radon rough-in in their building that somehow the radon's been taken care of, but it hasn't. So it's just the initial phases. Still needs test. The end goal of the building code changes, and by that by change I just mean the radon rough-in, is that they intend it to be easier and more effective to retrofit a depressurization system into the building than if there wasn't a radon rough-in system already there. And that's partly true. You know, in reality, we do find that there's some defects with how these rough-in systems are being incorporated or built that make them less effective and more difficult to actually use than starting from scratch. Unfortunately, that's still a thing. But in some cases, it does make sense. They do work, and when they work very well. So the whole goal, I think, for everybody should be, how do we make these radon rough-in systems work more routinely so people can use them and leverage them? And we'll talk some of those things that we could do differently in this presentation. Oh yeah, you guys are all over the country, aren't you? Or are you just around BC?
From all over.
Yeah, okay, good. Right, from all over. So here I'll be kind of referencing 2019 National Building Code Alberta edition, but whatever 2019 edition that you're on, they're all coalescing around the rough-in requirements in the 2010 National Building Code. And most provinces have adopted some version of what Alberta calls timely code adoption. I was at a conference in Ottawa just a couple of days ago from the Canadian Home Builders Association, and it sounds like most provinces are gravitating towards a system where they put more effort into kind of lobbying and getting their voices heard on the National Building Code. And most provinces want to adopt the National Building Code within 18 months of it being changed. We know there's still some that are lagging a little bit behind. I think Ontario would be one, Quebec I think would be another, But slowly, I think we're going to see all the provinces just National Building Code comes out and they just adopt it as their own. That's very different than how it's been in the past. I'm sure everyone here knows that one. But anyways, in 2010, National Building Code was amended to include radon rough-in requirements for the first time, and most provinces are using some version of that. So, back in 2006 and earlier, there wasn't really much for soil gas control in the Alberta Building Code or any building code, except maybe Ontario might have had a few things at that point. But nowadays, I think pretty much all the provinces are having some version of what's on the right-hand column here, which is clean gravel, poly under the slab, something about sealing the perimeter and penetrations. There's typically a radon pipe that's somewhere under the slab. It's labeled and capped, maybe in the sense that for BC, it's not capped, it's run through the roof as sort of the idea of being passive stack, although they don't like to call it passive stacks, they like to call it extended rough-in. And the sump pits where they're present are airtight. And that's kind of the page that most provinces are on at the moment, except for maybe a couple of places in BC that use a SB9 and have some slightly different criteria for the radon stuff. This is what's coming from the appendix in the building code, and we'll take a look at this later. This kind of forms the only visual reference to what the building code is asking for, and it doesn't tell the full story, and it actually is a little bit misleading, but this is kind of what people think of when they see radon rough-in. They see this stuff, a pipe, a stub that's capped off, something's underground, clean gravel. This is what they see. In reality, to make an effective radon system, you have to be very careful with some of these details. I think we'll take a look at a couple of these. So I guess the code reference here, 91343, would be Alberta, so it could be slightly different in different versions of the code across the country, but there's some requirement for ground cover, usually a granular material. I think the definition, though, is consistent across Canada at the moment, and what it says is clean coarse granular material having no more than 10% pass a 4mm sieve. I think that might be the definition across Canada everywhere. If it's different where you are and you're listening, yeah, just unmute yourself and let me know what your definition is. But I think that's the definition across Canada. That's actually a very broad definition, and it doesn't necessarily result in excellent gravel for radon mitigation systems, which really want the maximum amount of permeability or porosity so that we could apply a pressure at one point in the slab and depressurize the entire slab. So a couple of interesting things. Clean, coarse gravel. Let's start there. Clean, not washed. Some people call it washed. Typically it wouldn't be washed, it would be screened and not washed. Coarse just means that it's big, but that's not a good definition of the size, is it? Coarse, is that sand? Would that fit? Would that pea gravel, is that coarse enough, or does it have to be larger rocks? And if so, what size range? It doesn't really say. It does say a maximum of 10% passing a 4mm sieve. It gives us that. So we know that at least 10% of the material by weight and no more than 10% can pass a 4mm sieve. So that stuff that does pass could be 3mm, that would make it. It could be sand, between the sizes of 1 and 2mm, or it could even be silt or even clay, 10% by weight, not by volume, by weight. So that's an interesting definition. It doesn't say anything about the distribution of sizes of the particles larger than 4mm either. And that's important because if you want to maximize the pore volume, the porosity of this gravel layer, you would actually make them all round, not fractured, and you make them all the exact same size, like marbles. If you put marbles together, you would have almost 50% void space between those marbles, and you'd be able to pull air very easily along. But if you had small marbles and then larger ones and larger ones and larger ones, and they would all fit together actually, and your overall permeability and porosity goes way down, which could hinder the ability of that material to form an effective gas transfer area, or maybe even hinder its ability to form a proper capillary break, which is actually the main reason why we have gravel under our slabs in the first place. So there's a lot of loopholes in this current definition of granular material that aren't addressed right now, and I don't see them being addressed in the future, but I wonder about them anyways, because all gravel is not equal for the purposes of radon mitigation. Yeah, there we go. Minimum of 100 mils of granular fill material under the slab and less than 10% passing a 4 millimeter sieve. Yeah, that rock has been outside and it's been washed, but that's typically something like what we would see, a dirtier version of this, what we would see under a slab, at least in Alberta, most of the time. And it's reasonably good, reasonably good. There's performance options as well in the code. I think our code at some point had moved to an objective-based code, and I'm sure some of you guys are way more familiar with that term and what it all entails. But the idea is the code is no longer just prescriptive. Just do this, or do this, and you are good. Now the code is objective-based, so that you can actually propose something and convince your authorities having jurisdiction that your proposal, what you want to do, although it differs from the prescriptive version of the building code, you can make the case that it's just as good or better, and it might be accepted. And there's a product like this radon guard here that I'm showing that spent the money to get CCMC approval, had it tested to prove that it would perform as well or better than gravel as a granular material, and they got it approved. So this is an example of a product that you could substitute instead of gravel in projects without really having to convince your authority having jurisdiction too much, because they got the CCMC exemption to state that, hey, this product functions as well as gravel. So generally you wouldn't have a lot of pushback if you wanted to use something like this. But I think you could propose other options as well and make your case that it performs as well as gravel, all because our codes are now becoming objective-based to meet objectives, not prescriptive standards. There's an air barrier required under slabs in building code almost everywhere, except perhaps Ontario, parts of Ontario, maybe Quebec. And there's not a lot that it talks about. Generally, people would interpret this to be a 6 mil vapor barrier that same stuff you'd have on the wall. You would just put underneath the slab. And that's generally accepted. When you dig into it a little bit deeper, it's kind of interesting because that type of poly that's on the wall does not have a rating. What is it? I think it's UL 1745 or something. Poly in contact with the earth. It's actually not tested for that. So technically, we wouldn't know the long-term durability of poly that came off the wall just being used on the ground. There is a standard for that. Like I said, poly in contact with the earth. But nevertheless, common building practice to see poly that came off the wall used for underneath the slab. And I confess I've dug so many holes in slabs and seen poly that's 30 years old, 40 years old. I don't see any evidence of deterioration, even with the absence of that proper rating. But anyways, limited number of homes that I would have inspected for that. But generally, we'd have some kind of a poly. Here you can see they've taped the seams. We wouldn't normally see that in residential construction. Quite often it's just overlapped. Sometimes it's taped on commercial jobs. This one's interesting because you see how they taped it to the wall. I don't love that detail, because the slab, it looks like the slab thickness of 4 inches probably here, will not get over the top of that taped slab or poly area around the perimeter. So you're going to see some poly sticking up. I've got a drawing later on that shows how I just find that poly gets damaged during the concrete floating and troweling process. So I don't love that detail, but this slab looks like they really intended to make it well sealed. The idea is that if we can stop the radon from coming through to the concrete and going around the concrete, then we fix the radon without even starting. It's not necessary to put a depressurization equipment on a house. In reality, it's much more complicated than that, and we do find that small gaps open up, the concrete does shrink and pull away from the edge, and things aren't sealed quite as well as they should be. And so generally it's all hands on board, and I think every barrier we can put in between the ground and the occupants in the house is all helping to contribute to a good radon environment. But there's definitely no magic bullet, and sealing radon out is a very difficult exercise. I have not seen anyone be successful at the moment, but we're trying. We're going to try and figure this out. Yeah, this is that example that we saw on the previous slide here, where that poly is going up the side of the foundation wall. And I see this a lot, and I did this mistake in my own house. I did that. I carried the poly up the wall, and sure enough, yep, unintentionally or whatever, that power trowel and the guys on their hands and knees with their normal trowels. Trowels are very sharp, as you know, and when he's troweling around the perimeter, that poly just gets cut. And unlike this photo, or this drawing, which looks like that poly and the slab and the foundation walls are all tight together like a sandwich, what happens is the slab shrinks and pulls away from the wall, even an eighth of an inch, and we end up with gaps where the radon just goes around the poly and into the building. This detail here with the poly sealed to the footing underneath the slab, actually, if I could go back in time and redo my house, I probably would do it this way, because now it's formed kind of a sliding seal. That slab being squished down on that bead of caulking on top of the footing. Now the slab can move all at once, side to side, eighth of an inch, but it's maintaining kind of a gasket. So now that caulking, that red blob you see in the diagram, that's caulking, is now acting as kind of a gasket. And I think it could withstand an eighth of an inch of a slide over top and still maintain that seal. So I think this would have been a much better seal in my house. This detail is getting kind of more complicated because the building codes are more and more asking for insulation under the slab. And I had 4 inches of insulation underneath my slab, and it's becoming more and more common to see insulation under the slab. And I think that's a great thing, because that insulation is acting like the gasket. You could imagine the insulation resting on the edge of that footing, and the slab sitting on top of the insulation, pushing down. It was quite heavy. It does form kind of a good seal. And then when the slab shrinks and pulls away, it's sliding over top of that compressed insulation and still maintains a pretty good seal. So when I go and mitigate a new, or not a new, an existing large house where on the surface you might think, wow, we're gonna have a tough time creating a depressurization of this large house. Quite often those large houses have in-floor heating. And when they have in-floor heating, they usually have insulation under the slab. And I have seen large gaps around the perimeter, maybe even a quarter of an inch, similar to what's drawn in this diagram, and yet very minimal slab edge leakage, because I'm attributing the insulation is acting as a compressed sort of gasket around the perimeter. So everything's evolving, and that's all we can say is everything's changing. It's a moving target. It depends on the energy codes and how they affect insulation under the slab and stuff. This is what we see most of the time, is just a bead of caulking around the perimeter. The building code talks about the edges of the slab being sealed. And we're going to see later on how this approach always fails. I've never seen one that has not failed, because we're not sealing that joint, that slab to wall joint, as a moving joint. We're sealing it as a static joint, or a joint that's not moving, and we just apply a bead of caulking, whether it's a thin bead or a thick bead, whether you tool it with your finger or you leave it as a big gob. Doesn't matter what we do. When that slab moves an eighth of an inch, or even though we're using an elastomeric caulking that should accept movement, there's actually more to building a joint that is expecting movement than just using a flexible sealant. And that blows people's minds, because we just think we use a flexible product, it's always going to work, but it's a little more complicated. And I've seen 100% failure rate. You could do both. If the building code talks about sealing the perimeter, we could apply some caulking around the perimeter to meet the building code intentions, and we could also seal it to the top of the footing, where I think it would operate as an effective seal. So I'm not sure. We have to just keep working forward. But regardless, as you know, on all these polys, no matter how beautiful a job you do, quite often we did a poly job way back when, and for whatever reason, we came back 2 days later and we collected all this stuff that was on top of our nicely done poly, right? And we didn't show all the holes in it, but you can imagine you start dropping cigarette butts and screws on there, you're going to have holes in your poly. And as everybody knows, usually the concrete guys will deliberately, with their shovel, but completely right in front of you, spear the poly with their shovels to allow the excess moisture to drain away from that concrete and make that slab cure faster. That's also very common too, and having big holes in your poly doesn't help too much. So it's difficult. Poly is a work in progress, shall we say. We talked about the slab to wall joint being caulked. just showing here an older one. This is not new construction because that slab won't shrink right away. It takes up to about a year and a half for that crack to fully develop. So you won't see this at the time of construction. You won't see it at the time that this slabbed wall joint is being caulked. It will look perfect. It'll be nice and tight. It's so easy to caulk. You just dispense your caulking and run your finger down it, and it looks like it's a perfect job. But a year and a half later, this is what happens. It pushes out 1/8 of an inch and just rips your caulking right off the wall. Even when we use a material like this, an elastomeric polyurethane, look, this one has 100% joint movement. That means that, if the joint is an 1/8 of an inch wide, it could move another 1/8 of an inch and still maintain its integrity. But in order to create a joint that can accept movement, they have to be built in a very certain way, and that's kind of a longer story. And from what I've seen so far, no one is building a joint in that way. They're always caulking them as if they are a static, non-moving joint. They're just applying caulking. That's not enough. We need to have a bond break. Yeah, we need to have a bond break and create the conditions for which that joint can seal. It's more complicated. We could draw this later on in the chart. New construction says, hey, all the penetrations have to be sealed. And yet any house I've ever mitigated that has a bathtub or a shower, I would expect to see this. I would expect to see this hole going down for the plumbing to come through that slab underneath a bathtub or shower. This is a bathtub in this case. And honestly, only 1 out of 100 of these penetrations have ever been sealed on all the mitigations I've done. So if I'll ask you, if I'm mitigating your home, if you have a bathtub in the basement, you say, yeah, I've got a bathtub, and I'll be great. I'm going to cut an access hole in the wall so we can look in and seal that big hole that's underneath there. And the people are always kind of confused. What do you mean big hole? How do you know there's a big hole underneath my bathtub? I'm like, well, because 99 times out of 100, there's a big hole underneath your bathtub. And we cut the hole. Hopefully it's in a closet, 8 by 8, with a nice little access panel that goes over top, or we can put the drywall back in. And we look in there and they're like, wow, holy smokes, there is a big hole under there, right down to the gravel. I'm like, yep, it's just always there. Plumbers who come in to connect your new tub up, they'll find that bathtub rough in, take the lid off. You can see the remnants of a round lid that was on this hole. And they may have to chisel the concrete a little bit, depending on where their tub has to be aligned. They'll dig down, they'll find that plumbing that they're going to connect to. They'll fit this T going over to the tub drain and the vent coming off the top. But plumbers don't carry bags of cement with them. Plumbers don't carry spray foam with them. So I generally don't see any efforts made to seal this joint. Now, it is against the building code, I think, to not have a complete air barrier around around the house. So I think there would be a building code violation, but nevertheless, 99 times out of 100, this is what we see. And it's difficult for us to maintain depressurization under the slab when we have a big opening like that, where the air can just leak down. So it's important to seal it, and we seal lots and lots of those guys. I guess this could be a bathtub rough-in, I'm not sure. That's probably the toilet there with a 4-inch stack. It's probably the sink over there in the wall. I don't see where the bathtub or shower is in this case, oh, you guys probably noticed that red poly. Well, you see a lot, or red tape. That, of course, is not approved for vapor barriers, but it's very common to see it used on vapor barrier. Nowadays, we see the blue tuck tape, right? And that stuff has whatever proper approval it needs. This red stuff is still very sticky, and it looks like it holds pretty good, but the blue stuff is even stickier, as you know. When we're mitigating houses, we'd see stuff like this. So on the right-hand side is kind of a plumbing clean out. This one looks like it had a wooden lid on it that's removed to look in there. And that wood around the perimeter is probably starting to get pretty rotten. Sometimes the lids are okay, because the lid in this case, this is probably from the 70s or something, that lid would be made of plywood. And as long as the homeowners didn't cover it with something, it looks like in this case we could see maybe some mastic around the perimeter. I can see some lines on the concrete there, maybe where some mastic used to be. So if they had this covered with linoleum or something, probably that lid was rotted out as well. But if we see a plywood lid just sitting in the middle of the mechanical room, quite often it's actually pretty good shape after 40 years because that plywood can dry to the inside. So even though we're trapping, 100% moisture below that lid, and all that perimeter formwork is now rotted out, the lids are quite often usually in good shape because they can continue to dry to the interior. It's when you paint them or cover them with some impermeable material does that lid start to rot out. Typically, we'd replace those with a plastic plumbing cleanout lid that we'd see in a modern house. We just remove all that wood and cast in with concrete a new modern sort of plastic lid on top of that one. So I like the fact we're using plastic ones nowadays. That's for sure. On the left-hand side, this would be some kind of probably a rural property, and we can see some of the lines coming from the well. That looks like well pipe there, 1-inch well pipe, and you see it sleeved in a perforated weeping tile. I'm assuming it's perforated. I wonder if that red stripe means it's perforated, or maybe that's not the case. But typically these are perforated, and in this case could run either just outside of the building, or could run all the way to the well, making a really nice radon collector. So things like this in new construction have to be considered as well, and they'd be big radon leakers also. So ideally what they would have done is maybe carefully cut that weeping tile right back flush with the slab, and then find some way to seal the air away right where that well lines come through the slab. That'd be much better, because these would be really big radon collectors the way they're showing. There's a requirement in the building code to have a pipe inlet and outlet, as we saw in that diagram earlier, and quite often these are not done in the right place. They're crooked. There's all kinds of issues. I think I have some photos here. Let's see. Yeah, so the building code, as we saw this picture before, just kind of shows this nice, clean, easy system. You'll notice a few things. The pictures on the right-hand side are generally what's in there if the radon rough-in is located near the center of the floor slab. And the idea is that that we want to apply our suction to the center of the floor slab. That's the idea. And that's why underneath the two pictures on the right, there's no elbow and there's no length of pipe attached to those rough-ins, because they're already at the center of the floor slab. So if we were to cut off that top of that pipe and connect our depressurization equipment to it, we're already sucking from the center, so there's no need to have a pipe and an elbow directing the inlet elsewhere under the slab. I don't see these too often. I don't see rough-ins being located near the center of the slab, but the building code just says, hey, if it's going to be, you don't need to put an elbow on there. Those would actually work pretty good, because I could cut the top of that pipe off. I could reach in with my hand and I could dig out a handful of gravel, or a bucket of gravel would be even better, a 5-gallon bucket or 2 5-gallon buckets of gravel. I could dig that out, and the system would breathe and work really good. I've got a slide on this maybe next. On the left-hand side, we have some challenges, because this pipe you can see has an elbow and a little length of pipe attached to that, supposed to extend towards the center of the floor slab, although in reality I've never seen more than one joint of pipe on the end of that elbow, so it's always 10 feet away, which may not be near the center, but that's what I always see, 10 foot away. On this one though, you notice there's gravel also right at the face of that pipe, and what they don't show you is if there's gravel at the face of the pipe, there's gravel in the pipe, and that's a real problem, probably the primary reason why we abandoned 50% of all radon mitigation rough-in systems, because the pipe is plugged with gravel. You can see that next. And there's no easy way to reach down 10 feet and pull gravel from the end of the pipes. That's a big deal. Second thing is, you'll notice that this radon rough-in pipe is hugging the bottom of the slab. So we have a 4-inch pipe and a 4-inch thickness of gravel. And so that pipe is located right in that gravel layer. That's how it's intended. And that's the layer that we're depressurizing. So that makes sense. But in reality, because plumbers are putting in this pipe, plumbers aren't used to putting in pipe directly into the slab in that gravel layer. They know that they have to have slopes on their pipe. So the plumbing in your basement is quite often quite deep below that gravel layer, not inside that gravel layer. It's deep, it could be a foot deep, depending on how far the runs have to be. And there's no real requirement for the plumbers to have any particular elevation under the slab, I don't think. So they're typically below that granular layer that's used as a capillary break and a water management layer. But for radon system, it has to be in that gravel layer, right tight underneath the slab. So the other reason why we abandon a lot of radon mitigation systems and stubs is that pipe is maybe a foot deeper than it should be, or 6 inches deeper. And at any rate, the open inlet of that pipe isn't even in the gravel layer anymore. It's below. So we really can't even guarantee that the water isn't going to be completely submerging our pipe because it's deeper than the water management layer, which is that 4 inches below the slab. So that's the second most common reason why I would abandon radon rough-in systems. Here we can see that the pipe is off the footing, and actually if they built it like this, it would probably be usable. But in reality, what we get is these radon stubs coming through the slab right tight against the foundation wall. And then the frost wall, the 2x4, 2x6 frost wall is kind of enveloping it. And it's much closer to the foundation wall than what's shown here. Can be an issue too sometimes. Here's what I see in reality. I took that picture on the left of a screenshot from a video I had shot, and where I went to a house under new construction. I located the end of the pipe and I kind of exposed it to see what it looked like. And yeah, sure enough, the end of that pipe is filled with gravel. So how am I supposed to move some amount of air, 20 CFM, 50 CFM, whatever it is, how am I supposed to move air into the inlet of that pipe when it is not only, it's plugged with gravel. The gravel is inside the pipe. It just is not going to breathe very well. It's like drinking a milkshake and you got a big blueberry stuck on the end of your straw. That's exactly what it's like. You really can't get any milkshake out of that straw, and I can't get any air out of that pipe. So that's a big reason why we abandon them. On the right-hand side, I just made a mock-up. I just filled the end of a pipe with some cement, and I pushed in some rocks, and just to kind of show how am I supposed to pull air through that thing. And that gravel that's spilling inside the pipe could extend 4, 6 inches or 8 inches into that pipe, and really makes it hard to pull any air. It's just, you can just imagine sucking and wheezing on that pipe. So we need a way to prevent this from being obstructed in this way. Now, for commercial buildings, we could take a cue from them. They typically use a cage. So there's a metal cage. I saw a lot of them on my website actually for commercial construction. It's just a metal cage with an expanded metal mesh around it, about 18 inches in diameter. And the pipe just goes inside this void area, and all the metal mesh holds the gravel back. And so when I suck on the pipe, I'm sucking in this empty metal cage, and all the gravel is held back by that cage. And because the surface area of that gravel around the cage is so large, it has no problem pulling the amount of air that it needs to. It works amazing, but it hasn't caught on for residential. What I sometimes see is perforated pipe being used on the inlet of that pipe to prevent it from being blocked. And that seems to work pretty good. I think that's good second best. So perforated pipe, a loop of that would work good. That's kind of a floor plan of my house and how I potentially could have run weeping tile or in a loop over to a fictitious rough-in. Would have worked very well. They could just do this. They could have a riser sticking out of perforated pipe in a loop around the building. I think that would work pretty good. And I think the building code supports this, doesn't talk about perforated pipe, but I took the trouble one time to add up all the area of these slits that are in this perforated pipe, and you can kind of see the perforations, at least in the top face of this pipe here on the left. I can see them, just make them out. And I added up the area of those little slots, and I found that in a 9-foot section of pipe, the open area of all those slots in the 9-foot section would equal a 4-inch opening, like the open end of a pipe. So I think as long as a guy has at least 9 feet of perforated pipe on the end, you would meet the requirements for the total opening to equal the open end of the 4-inch pipe, which is shown in the building code. And of course, if you made a big loop that went around the inside of the building, obviously you'd have a lot more than 9 feet, and that probably work awesome. They're often not straight, so it'd be nice to have them staked in the ground, nice and straight, because when Schedule 40 pipe is rigid, it's very stiff, and if you have a crooked rough end, you can imagine how hard it is to straighten that out and make it look good. If it's crooked by exactly 45 degrees or exactly 22.5, okay, no problem. There's fittings for that. But more likely, it's 10 degrees off. How do I straighten a 10-degree pipe? Other thing we see quite often is the pipe coming up through the slab is not Schedule 40 pipe. It's not ABS pipe. It's not Schedule 40 PVC. Instead, it's SDR 35 sewer pipe, that thin wall sewer pipe that is not approved for use above ground. Although if you're listening from BC, I have never seen a passive stack in BC yet that wasn't completely constructed out of SDR 35 thin wall sewer pipe, right through the interior of the building and right through the roof. I'm sure they exist, but most of them seem to be using this pipe that isn't allowed above ground for some reason. So if we see that pipe, generally we would cut the rough-in stub off 1.75 inches above the slab, and we'd add that transition piece that you can buy that glues over top of that SDR 35 to convert it back to a typical Schedule 40 size, and we can continue with Schedule 40 piping from that point. The building code talks about the outlet of this pipe being capped, airtight, and labeled, except in BC where it would just extend right through to the roof as an extended rough-in. And that's pretty straightforward. It's capped, airtight, and labeled, but we don't typically see that. Instead, we see, temporary caps quite often, the majority of the time, on the radon rough-in stubs. And temporary caps are a challenge because they split, at least that one on the right. Those pretty much always split. They last a couple of years, but they tend to start splitting and they open up very easily. And you don't want to open the top of one of these rough-ins out without actually connecting equipment to it, because it has a beautiful radon collector beneath that radon cap, and all that soil gas is waiting to get sucked into the building. So a broken cap is not what you want. And sometimes we'll see some humorous labels like on the left saying the radon has been removed. That's interesting. That was clearly not the case, but that's very misleading for homeowners. And we'll often usually see radon spelled R-A-Y-D-O-N, and we always get a good kick out of that because we always wondered who this radon guy is and why he can't make a good rough-in. Oh, here's one, not a sewer line. Well, you know what? This guy at least is thinking ahead to something that could happen. He's using black ABS piping and stubbed out of the ground, so he's making it very clear this is not a sewer line. And I've never seen one in person, but I have heard that there have been, toilets connected to radon rough-in systems. And I don't know how many times you could flush a toilet that just dumps into the gravel below the slab, but you probably flush it 10 times or something. But that would not be a pretty thing to have to fix. Some pit covers are required to be airtight as well in the code there, and they rarely are. I don't see too many sealed sump pits, and that's a shame because a sump is often an amazing radon collector because it will have perforated pipe coming into it, sometimes in 2 or even more pieces of pipe, often in loops. It will even extend outside of the house and go around the outside of the footings. So it's collecting radon from a really big area, brings it into the house, and then if it's not airtight, that radon just moves into the house like crazy. And oftentimes you can even put your hand in there at the perforated pipe and feel a breeze on your hand. There's a lot of airflow coming in. So we see something like we do on the right here, which are a big horseshoe-shaped kind of lid, a big cutout on the lid, completely not airtight at all. That's quite typically what we would see. Sometimes we will see something like on the left where they've used a lid that is potentially airtight, potentially has a gasket. We can even see a cord grommet there. That looks really good, but when you look closer, almost never do they apply the gasket around where their pipe comes through the lid. And here you can look down, you can see, oh, there's a 1/4 inch or 3/8 of an inch of the space around that pipe in the lid. And really what they should have done is apply a gasket to that. There was a study in Winnipeg in 2012 of, I think, a dozen show homes, and they were assessing at that time how closely these show homes were compliant with the then brand new 2010 National Building Code requirements. And they had different levels of compliance with things like sealing the slab and the poly vapor barrier and the clean gravel, different levels. But with the sump, it was unanimous. Not one sump that they inspected was actually airtight. And that's been my experience as well. I've never found a truly airtight sump. Actually, I shouldn't say never. No, yes, I have seen them, but they're few and far between. And usually it's something like this. And to find a gasket below the lid is pretty rare as well. Yeah, and that's an example of this is more of a retrofit kind of a lid, where if we found a sump that was not airtight, something like this could be applied, it could be glued and screwed to the floor, has a gasket, the lid is removable in two pieces. All the fixed stuff that's coming through the lid, like the cord and the sump piping and the radon system, if necessary, would come through that smaller fixed portion of the lid, and that larger clean opening there at the top could be removed at any time to inspect the sump and work on it. So that's what we'd have to apply if we don't see an airtight lid at the time that we're mitigating. So again, you look at this diagram in the back of the code, it just seems so easy. It just seems like, yeah, how could anyone get this stuff messed up? But stuff is trickier in practice, and radon is very nuanced. So it is pretty easy to leave gaps, to put the radon rough in too low, not have the right kind of gravel. There's so many different ways where this vision can't be realized. And usually it's human error, or maybe it's an education issue. So again, it seems so simple. Clean gravel and poly and everything's sealed up, and a radon pipe under there, and capped and labeled, and airtight sump lid. But in practice, it's not simple at all. And there's so many different ways that each of these criteria can be compromised in some way that ends up providing pathways for radon to enter this house. And lots of new homes have high levels of radon because these items aren't being done sort of effectively enough. And also, the public thinks that because they have a radon rough-in, that somehow the radon is no longer an issue. That's the other thing we have to battle. Whereas the radon rough-in is just there to kind of give you a head start towards an effective mitigation. And it'd be nice if we could make it so we could count on these rough-ins as well. Yeah, and as always, don't take anything I say to heart. Let's always check with our authority having jurisdiction, because they ultimately have the final say. So they're obviously your best friends. Yeah. If levels are still high, though, after occupancy on these new construction, the good news is that it's still fixable, even if every single element of the radon rough-in in the building code is done improperly. Even if that's the case, a professional mitigator, a certified guy, can go in there and fix that house anyways. But it would be nice if we could leverage the advantages of the poly, gravel, and the sealing, and the rough-in pipe to make the system as effective as possible, but they can still make it work. Yeah, okay, thank you for that. I hope that was interesting for you, and I'm glad we got some time here, 12 minutes. I either want to draw something for you to show you the basic kind of physics of how we design radon systems that work, because that kind of feeds back into the building code discussion, or we can field some questions. Either way, let's do that. So let me.
Okay, Colin, that was absolutely excellent. Claude, were there any chats before we try to open up any conversation?
No, I don't see any chats posted at this point.
Okay, so I have a couple questions. So this authority having jurisdiction, so one of the challenges that we have in First Nation is to educate and help build First Nations governance to understand the authority having jurisdiction. And one of the things that we're pushing hard is, you're the authority having jurisdiction. You need to make decisions regarding your radon gas in your Indigenous communities, because by location, many of the First Nations are in extremely high radon gas areas. So this is one issue that's I personally find baffling, but it's a challenge. Is they, exercising your authority, having jurisdiction. Like, why are you building? Like, you don't build a canoe with a hole in it, right? You build a canoe that's going to float, that's going to be safe. But we're building homes that leak.
Yeah. Yeah, that's true. And I think in Europe, they do make an attempt to actually seal radon out, which I've never found to be effective, but probably only because we're not all working on the same page to make that happen. But in Europe, I see them welding the seams of their poly. They don't tape them or caulk them. They actually run a thermal welder along and they weld them on the corners. They have preformed corner pieces that they weld together, and the poly is almost never attached to the foundation, the sides of the foundation wall. They're actually extending over top of the footing, and the walls are placed on top of the poly. So they do everything in their power to create a system that's airtight from the start. That's very difficult, and we're not quite there yet, but it's a good goal to try, anyways.
Oh, and I have a couple of questions for you.
Yeah.
First one, how many passive systems fail in a percentage wise? Is there an actual number that we're seeing with passive systems that are, I'll qualify that.
Can you back up and explain passive systems for people?
Well, that's a very interesting question. The question was how many passive systems fail? I won't be able to give you any kind of information on that at all, but your question is interesting because what's the criteria for passive systems failing? There's no requirement to test for radon. So of all the houses that are being built in BC, for example, with passive systems at the start, none of them are required to test. So of the small percentage of people who test for radon after their house has been constructed, what percentage of those ones come back high? I think that's what your question. That'd be very interesting to know. I don't think we have that information. The federal government is pushing to include passive systems in all new construction, kind of use that BC model. And the data that they've got is that passive systems on average, results in a 40 to 90% reduction in radon levels compared to if there was no passive system. I think the research is still ongoing. An interesting question would be how many passive systems would fail if they were required to be activated? Because remember, there's a lot of places in BC that are very high in radon. So you could have a place that would have been 800 becquerels per cubic meter were there no passives, if it was just a radon rough-in stub. But because they brought it through the roof, let's just use the federal government's example, it's half. So now the house is still at 400. Well, 400 is still double the action level for Canada. So that would be a fail. So the next obvious intervention would be to activate that rough-in system and put a fan on it. But if we do that, we're going to run into the same problems that I run into every day with that rough-in being plugged and filled with gravel or too deep, and those kind of issues. So how many passive systems fail is kind of a loaded question to which there's no answer right now. I prefer that we get the foundation built properly before we go too crazy with adding other criteria onto the radon stuff. So for example, can we make it so the radon pipes are not plugged? Can we all agree that we need to put a cage on the end or a perforated pipe, or can we all agree on doing something to prevent gravel from entering the end of the rough-in pipe? If we can do that, then they can be activated very easily and they probably work a lot better. And if we could agree on different methods of sealing to prevent the leaks underneath the tubs and from around the perimeter, now we're getting somewhere, and we can layer on passive stacks on top of that, and we probably get better results. Active systems would be better and easier and faster. But I just think we're sometimes jumping ahead and adding more criteria onto this rough-in without looking at the issues that we currently have, like the plugged pipe, which bothers me the most, as you can tell.
Which brings me to two other sort of like thoughts and what your thoughts are. I'm finding in BC in Zone 2, in our building Zone 2, which is primarily interior and the north, we're required to install radon systems, not in Zone 1, which is down on the coast. Now, the building officials are requiring that the passive systems have a pipe that vents at the roof for the passive systems. And in this jurisdiction, they're allowing two things. They're allowing you to cap the top of the pipe at the roof level. Not sure why. And the second thing is, if they are suggesting that you have the system active, they're requiring two 90-degree elbows for a candy cane at the top of the pipe. Now, I note from our CSA standards that we're we're not advising to do that. Now, I'm basically asking you what your thoughts are on those two items.
Well, actually, you said a lot of interesting things there, more than two. The first interesting thing you said was they're requiring it to go through the roof, but actually, the building code doesn't say that. There's a performance option in that same section you're talking about that says or it says or like go through the roof or terminate outside in a manner that does not create a hazard. And it's funny that one just gets discounted because I guess it puts too much onus on the building inspectors to make that decision. They don't feel comfortable making it. So maybe that language needs to be tightened up to describe what terminating outside in a manner that doesn't create a hazard means, because no one seems to be willing to take that risk. It's in there, the clause is there, and you might be a builder and say, hey, I want to terminate out the sidewall. We're out in an acreage, there's nothing there, and there's no windows, and there's no people, there's no nothing. And yet their building officials aren't even recognizing that as an option because they don't want to go on any kind of a limb and say, well, I agree that that is outside in a way that doesn't create a hazard. So I find that that's the most interesting thing that you said straight off the bat, that whole clause
that's an issue.
is just being ignored. Second thing was the gooseneck. We don't advise a gooseneck of any kind in a radon system, generally because of the likelihood of freezing, and certainly in a passive configuration and even with an active configuration, the more surface area you expose this pipe to, the more changes in direction. I mean, a candy cane coming right over back over the top would probably be expected, depending on the airflow, to start to condense. Because remember, this moisture, this ground air that we're pulling out, and oftentimes it's got a lot of moisture in it, maybe even close to 100% humidity. So once it goes through the roof and now it's -10 outside and -20, and it's traveling around that corner and that cold, cold pipe, it starts to freeze and condense. And next thing you know, boop, it's plugged completely off and you have a completely plugged gooseneck on the end. It's interesting they require a gooseneck or a candy cane because the fan manufacturers don't. The fans are rated for water and condensation flowing back through them. They're rated for it. There's even condensation bypasses a person could buy if they were really interested in condensation that captures the condensation trickling down the pipe and reroutes it through a tubing to the other side of the fan. That's a common method of handling condensation issues. So to just blanket require a candy cane and blow this humid air back down on the roof decking, that doesn't make a lot of sense.
Well, what I'm finding is that what we're, as professionals with karst, I mean, we are trained in these areas, and I'm finding that the building officials are not trained. They don't have an understanding of it, but they're just insistent, and you could get two different opinions from two different officials on any particular site, right? It's very difficult. And I know you said earlier that you're involved in the new standards, and hopefully we start to employ the CSA standards within the documents of the building code, which will be really helpful.
It's possible, but it's always an education issue as well. And I remember one time, I think it was at the beginning of COVID. No, it wasn't COVID. It was before that. There was some kind of a downturn and there wasn't as many building permits going out for some reason. And I was doing a mitigation. I said, you know what? I should invite some people from the building officials to come down and check out a mitigation. So I put a call in Calgary and I said, hey, do you want to come down and see a mitigation? I'm going to show you how we activate these systems and some of the challenges we're finding. And to my surprise, 14 building officials came down to my mitigation. 14, I got some donuts there, and they were there for an hour and a half or something. And they just considered it part of their education. And it was great. They had awesome questions. They were interested. And when I showed them some of the challenges with activating these systems, I really felt it made a big difference because remember, these guys, they don't just know the code. They go to seminars. They learn about these nuances and stuff like that. So they need to learn from us. And just referencing codes and other standards may not be enough sometimes. So it'd be nice if we could help educate them and bring them along. They all seem to be great people, and they just need to be educated.
Absolutely.
On the nuances. That's all.
Yeah, I think that's where we're heading to, is to, increase the education for those people that, have the authority of having jurisdiction. Myself being a building official, we don't do too much on that, and we need to open that type of dialogue within our group on radon. And maybe that's something we should, at this end, I should talk with our liaison and see if, we can get karst involved in that too, right? To we have situations where they're still using above ground, they're using sewer grade pipe less than Schedule 10, and that's being run all through houses right up to the roof, right? Things like that, right? So,
Yeah, we see that all the time. Well, it's
Yeah,
ironic. It's
in our
ironic, that
in our code at 913, it just simply says it has to be 4-inch pipe. I've even seen corrugated 4-inch pipe being used to go because it just says 4-inch.
well, maybe that's kind of a breakdown with the building officials then to some extent, because it's funny that because the code says, you're saying it says 4-inch pipe with no other explanation. It's funny that what they would agree that it is appropriate would be a 4-inch pipe that has no above ground rating, that is prohibited from being used above ground. It's funny that they would say, oh, because it says 4-inch pipe, it could be any 4-inch pipe regardless of its suitability. Could we make
That's
it?
exactly what they're saying, Colin. And interesting enough, I phoned and had a conversation with the Western sales rep from IPX, and he said basically before the Radon X pipe came out, and they have an actual designated pipe now that is for radon work. He said our specifications is that is to be used below grade. What anybody else uses it for is their business, but it does have a specification that sewer grade pipe be used below grade. That's their specification. But in a discussion with any building official, it's just simply, no, it's 4-inch, we'll allow it to be used. It's cheap.
Yeah, it's funny because the pipe itself is not permitted to be used above ground. It has no UV inhibitors. So if you went through the roof with it, it will harden and crack down inside the building, and the radon that you're pushing out will now push out into the building. So yeah, it sounds like just a breakdown with the building officials, I guess, a larger breakdown.
Education.
It's only education. That's all it is. I mean, look, the radon guys, we don't care. We've no interest in the type of pipe or the color of pipe. We just want it to be safe. And so having a pipe that's at least rated for, our code talks about DWV, so it has to be rated for DWV.
Final report in June.
Yeah, it just has to be rated for DWV, drain, waste, and vent. That's normal ABS sewer pipe would be acceptable. There's also
And CSA standard.
Yes, of course, yeah. Yeah, that's right.
That's the big one, right? So
yeah, we don't care. We don't buy the pipe. We don't supply the pipe. Radon guys don't care about the pipe, but we care about safety, and we recognize that most radon guys wouldn't activate a system like that. They'd insist that that pipe be removed. That's kind of a shame that the lowly mitigator is the one saying that that's not a suitable pipe. Doesn't feel comfortable activating it because it's too dangerous. Yeah, there's some breakdowns.
Yeah, I've been asked to certify systems like that, and it's just unfortunately through our standards set up by Karst, I can't do that, right? And that really opens a can of worms because there's a lot of plumbers out there here locally that are doing radon work that, there we go, same sort of thing that not educated, but
yeah. And as a practical nature, if you transition from that pipe to a Schedule 40 DWV as it goes through the roof, so you don't get the UV deterioration. If you could rationalize it that pipe is not in a protected location, it's running up a chase, so it's not likely to be impacted. I mean, we have to do stuff that's practical as well. So, I wouldn't feel comfortable leaving in that pipe, but I guess if I could be convinced that it is in place and it's safe, and it's protected, it's not being exposed to UV light. I mean, maybe there's some kind of disclaimer we could put on it. I hate to have to rip out 3 stories of piping that's hidden inside a wall because they use that type of piping. In the States, it's used quite frequently. And in Canada, at one time, I think we have a sentence somewhere in some document that says, it might have said Schedule 20 pipe could be used in an area where it's mechanically protected. But what's ironic about that is SDR35 pipe is not Schedule 20 pipe. We refer to it all the time. People say it's Schedule 20, but actually it's not, because if it was Schedule 20 pipe, all the schedules of pipe, Schedule 20, 40, 80, 120, they all have the same outside diameter. So you could use any fitting. But with SDR35 pipe, you'll notice it's smaller. So we still refer to this pipe as Schedule 20 pipe, but it's not. It's SDR35 pipe. It's different outside diameter than Schedule 20 or Schedule 40 pipe.
Colin,
thanks, Colin.
One quick question here. The question is, HRVs, are they effective in reducing radon levels?
Wow. Well, that's a quick question to ask, and it's a 1 hour long. What I can tell you is, I guess, a short story is that HRVs work to reduce radon by simple dilution. and they work by whatever air exchange rate this building already has. It's likely going to be unknown, but whatever air exchange rate it naturally has, just from defects in the building and air coming through, plus whatever mechanical exhaust and ventilation you currently have, if you double that number, the radon will go in half. That's just basic physics. That's the idea of how it works. The challenge is nobody knows what the existing ventilation rate of the building is. And it's also variable, it depends on wind and temperature and all kinds of stuff, occupant behavior. So while they are an effective, or they can be an effective technique to reduce radon, they mostly aren't, because people have no idea of how to assess the current air tightness. So for example, if I'm going to add an HRV with a capacity of 100 CFM, if the current building already has 100 CFM of air exchanges naturally through defects or whatever, then that building would drop in half, and then maybe that's enough. But if that building was really tight and it had 10 CFM of natural ventilation and I had 100, now it's going to go down by a factor of 10. But it's just as likely the building already has 200 or 300 CFM of natural ventilation and I had 100, and I only made a 30% difference. So the problem is the results are variable in every house, and you can't predict them unless you measure them. And I did do a 4-hour course on this at one time, and it's complicated. You need to do a blower door test to assess the air tightness of the building. You need to take that information and do a model. I use the Alberta infiltration model to assess natural infiltration. You have to add whatever mechanical ventilation you have, and you have to come up with a really good number for how much air you think the house is breathing right now. And only then can you assess the impact of adding another 100 onto that. So it's a long, complicated answer to say, yes, sometimes they're very effective and sometimes they're not effective. And generally people don't know how to discern when to use them. I'm also doing some experiments on ERVs right now, and I have a sneaky suspicion that this one ERV that I'm investigating is allowing radon to pass through the membrane. So, we're just starting to learn about HRVs, and that's becoming common language, but we're going to start to see more ERVs in certain neighborhoods, right, in certain regions. And those ERVs also pass humidity through the cores. So they preserve or deflect humidity from the indoor environment. And I have a sneaky suspicion that in some cases, radon is also able to diffuse through the core of these ERVs. And if that's true, then an ERV could not reduce radon because it will just pass through the core and come back into the fresh air stream. So it's complicated.
Thank you very much.
Okay. Well, it's been an interesting session. I think we could have gone for at least another hour here.
Yeah.
So I think at this stage, if anybody has any follow-up questions, to reach out to us, and then we can forward to Colin or reach out to Colin directly. And I know this is a big issue, radon gas, especially in First Nations. A lot of them are located in really high red zones, if you look at the map. So it's something we need to start addressing, and again, exercising council, who's the authority having jurisdiction, need to figure out how to deal with this now, right? So thank you, Colin. Thank you, everyone.
Thank you, Colin.
For,
Thank you.
attending, and until enjoy the weekend, and we're back on Thursday. So
Awesome. Well, thanks for having me.
Thanks, everyone.
Great chat.
Okay, bye.